Welcome to our first video in our Class 12 time series of lecture videos. Today we're going to be introducing the topic of polarimetry. So it's a technique that we use. We use instruments called polarimeters to assess whether we have succeeded in synthesizing pure enantiomers whose rotations for light have been documented in literature, or if we synthesize new stereochemical compounds and we need to document how much they actually rotate plane polarized light. At any rate, we'll start this lecture. For the most purposes, melting point, boiling point, retention time on silica gel, other physical properties, enantiomers have the same physical properties, except for two. And that's the way they rotate plane polarized light and the way they interact with other chiral molecules and or surfaces. Diastereomers do not have the same physical properties. So the first different physical property that I mentioned, enantiomers rotate plane polarized light in equal but opposite directions. So what do I mean by that? I mean, let's pretend we have a solution, some sort of solvent that's achiral is used to dissolve up a nice chiral molecule, and we put it in a cuvette of some sort with a defined length. And at one end of the cuvette, we have a polarizing filter. So light vibrates in all sorts of different directions, but our polarizing filter creates something called plane polarized light. So it only lets the light that's vibrating in the correct direction pass through it. As it passes through the solution of our chiral molecule starts rotating that light. So it interacts with the light and the light gets rotated. And so what we have to do after the light has passed through our solution is we have to have a second polarizing filter, and actually we start rotating that polarizing filter so we get the maximum amount of light to pass through it. And so at some rotation or degree of rotation alpha, we get our light that has been rotated passing through that second polarizing filter, and that's essentially what polarimeters do. So after plane polarized light passes through a solution of something chiral, like I guess we have as an example 1-chloro-1-fluoroethane, the second polarizing filter must be rotated to let the light pass. The change in angle called alpha is the observed rotation. So what are some other parameters that our polarimeters and scientists use when they're talking about these kinds of experiments? Well, the degree of rotation alpha depends on a lot of different parameters: temperature, wavelength of light, concentration, which we abbreviate as C, the length of the cuvette, L. So we define something called specific rotation, where the specific rotation alpha is dependent on a certain temperature and wavelength, usually 589 nanometers. The sodium D line is used, and that is equal to the rotation alpha that's observed divided by the length of our cuvette times concentration. Length is typically 1 decimeter, which is 10 centimeters, and concentration is typically given in grams per mil. So we look up glucose, and the specific rotation at 20 degrees C, and the sodium D line is plus 52 degrees, and that's a concentration of 1 in water. We look up L-alanine, and our specific rotation at 20 degrees and the sodium D line is plus 14.5 degrees, and that's a concentration of 10 in 6 normal HCl. And here is L-alanine, one of our amino acids. So these numbers are for samples with only one enantiomer present. Of course, the opposite enantiomer, so not L-alanine with the S stereocenter, but D-alanine with the R stereocenter, would give us opposite rotation at a concentration of 10 and 6 normal HCl. It would be negative 14.5 degrees. So enantiomers rotate plane polarized light in equal and opposite directions. The rotation would be 0. The observed rotation alpha would be 0 if the mixture is racemic. That is, if it has 50% of one enantiomer and 50% of the other. Because, like I said, they rotate light in opposite and equal directions. So we'll work a problem in the next video. Thanks for bearing with me in these lecture videos.